Hey guys, in this video we are going to talk about errors in polynomial interpolation. So we know that we are given a data set, we interpolate some type of polynomial for that discrete data set, right? So when you interpolate using a polynomial, we get error. So now we are going to discuss. Now we are going to measure that error, right? So let's get a function f of x defined on a b interval, right? Closed interval, and a set of and consider these x's. They are distributed distinctly, right? On a b interval, right? And we know that I runs from 0 to n. Let's consider this a polynomial Pn. So this polynomial belongs to the set of all polynomials with degree less than or equal to n, such that this polynomial interpolates at these points. So this polynomial gets the same value of function f at these nodes, right? So these two are equal. Now we can define the error function, the error between these two, f of x and the interpolating polynomial. So this is the error, right? So we can define this error function, which is the distance between these two functions on AB interval, right? And there's a theorem. So this is the theorem for error, right? So it says there exists some value psi on the interval AB. So here we don't know what psi is, right? But we can say there exists, right? There exists some value psi on this interval, closed interval, such that that error function is exactly equal to 1 over n plus 1 factorial times the n plus 1 derivative of f at that psi times the product of these linear factors. So this is true for all x on the interval, right? All right. So we are going to show this. We are going to prove this theorem. This is very important theorem. So definitely we have to find the error when you have your interpolating polynomial. So you should know how much error do you have, right? So that's why we use this theorem, is very important. All right, let's try to prove this theorem. So okay, the first case, if suppose this function f belongs to the set of all polynomials with degree less than or equal to n. So what happened? So we know that, so if this is a polynomial, n degree polynomial, or this is a polynomial, right? So we know that the previous we have shown that if you have n degree polynomial for this data set, for these n plus 1 data points, so we showed that that polynomial, there is no that polynomial is unique, right? Therefore, this P of x, P sub n, this polynomial and f of x are the same. Then in this case, the error function takes 0 for all x, right? Because of the uniqueness of the polynomial, right? Which is related to previous discussion, right? Right, I hope understand this. And if this function does not belong to the polynomial set, let's discuss that, right? And consider x, if x is equal to xi for some I, right? So then what happened to this error function? So we know that at these nodes x0, x1, xi, they are called nodes x0, x1. These are distinct x's, alright? So these are called nodes, right? So at these, if you consider one of these, say xi, right? So one of nodes. So we know that at each node, the interpolated function is same with the function value. So at each node, right, the error function is equal to 0. I think this is clear. So, and let's consider this one. X is not equal to any of those nodes, right? So x is not equal to any of those nodes for any I, right? So let's consider this case. So if x is equal to one of nodes, there is no error. Now let's consider x is not equal to any nodes, right? All right. So I'm going to define a function, right? In this way, I consider all linear factors. I consider multiplication of all linear factors. Here, how many linear factors do we have? We have n plus 1 factors because I runs from 0 to n. Here there are n plus 1 factors because here x minus x0 times x minus x1 times x minus xn. How many factors? Here you have n factors with this n plus 1 factors. So this one is a and what happened to the function w evaluated at each node? So because if you plug one of nodes, so this vanishes, right? So because one of linear factor becomes 0, therefore this one will be equal to 0, right? So we know that here we have n plus 1 factors, linear factors, then we get a n plus 1 degree polynomial from here. So this one is a n plus 1 degree polynomial in x, right? So when you differentiate this function, w function, n plus 1 times, so you get something, you get n plus 1 factorial, right? So right, these are clear, I think, right? So I hope you understand this one. So if you plug one of nodes, the function vanishes, and this is a n plus 1 degree polynomial. And if we differentiate and this one n plus 1 times with respect to x, you get n plus 1 factorial. This is clear. All right, I consider a fixed point y in between a and b. Here, let's consider a fixed point, a number between a and b, right? So y is a number in between a and b, and suppose that y is not equal to xi, right, for any I, right? So that means here, so here you have these nodes. Y is in between yep, y is a number in between a and b, but y is not equal to those nodes, right? So we can define this c constant as follows. So here, when you plug y into here, we know that this w function evaluated at one of nodes becomes 0, right? But if you plug y into here, that is not equal to 0, because that is not equal to 0, that y is not equal to any of nodes, right? That's why. So you can define this one, because this is not equal to 0, right? Let's define a constant as follows: f of y minus p sub n of y divided by w of y, right? Let's define another function as follows. So phi of xi, so here phi of x is defined in this way: f of x minus p of n of x minus c times w function, right? All right. When you plug xi into here, what happens? So we know that this w function vanishes when you plug xi in here into here, right? This becomes 0. So we know that this function, this is your evaluating interpolating polynomial, right? When you plug xi, one of xi's into here, so this takes the same value of function f. So this one also, this one also, this one is also equal to 0 when you plug one of nodes, right? So therefore this psi, the function psi, vanishes at these x's, right? Here, look at this. The psi function vanishes at each node xi, right? So therefore we can say these xi's are roots of this psi function. All right. So xi's are roots of xi's: x0, x1, dotted up to xn. These all are roots of this psi function, right? And what else? Here, notice psi function here. Just take a look at this psi function, right? Phi function, right? This is n plus 1 polynomial. This one is n degree polynomial. This one is n plus 1 polynomial. N plus 1 degree polynomial. This is n polynomial. Alright, notice those things. and when you plug these things, the function value at each node is equal to 0. Alright, therefore these are roots of this psi function, right? Alright, so when you plug y, let's plug y, this value here, y, into here, right? When you plug y into here, f of y minus p sub n y of y times c w of y, right? So what is the value of cw? Cw is f of y minus p sub n of y. Cw is this one cancels with this, right? You can cross that off because c times w of y is equal to the same thing here. Therefore y also a root of psi function. So how many roots does this function have? It has n plus 2 roots here. So this implies that psi has n plus 2 zeros, right, on AB interval. So alright, let's so here you have psi function. So this is your psi function, this is your x. So this function is defined on AB interval. So we know that here you have x0, x1, xn, and you have somewhere y, right, which is not equal to these nodes y, right? So all these points, these are zeros of this phi function. That means if you draw psi function, so that function goes through these, so that function hits at these points, right? This function hits at these points, x0, x1, xn, y. So this function intersects x-axis at these nodes and this y, right? Because they are zeros. Where's that? Yep, here. So because of that, so here look at, check this one here. So if you consider these two consecutive nodes or x's, right, so you can apply mean value theorem, right? So just look at these two x's. So notice the function of phi. So we know that this phi function hits at these points. So using that, now you can use a mean value theorem. So here the function value is 0, function value is 0. So that means there exists a point in between these two, right, such that the derivative of this function, this is phi, your phi function, right, the derivative of this function is 0 at that point, right? So that means if you differentiate phi, so that means the derivative of that phi function, there exists a certain point in between these two, such that, say, alpha 1, such that the derivative of that function at that point is equal to 0. So this one is parallel to this line, right? So how many alpha i's you can find? So here you can find at least how many? So here you have 1 2, so here you have n with this n plus 1 and with 5 n plus 2, right? So how many subintervals do you have? You have n plus 1 subintervals, right? So each subinterval you can find at least a point. So that means you can find so you have how, so here you have n points, including this you can have, if you include this then you can have n plus 1, and if you include y n plus 2 points, then you have n plus 1 subintervals like this subinterval here. This one is one of them, this one is one of them, n plus 1 subintervals. That means at least you can find at least n plus 1 alpha i's such that phi derivative of phi at those alpha i's is equal to 0. That means phi prime has at least n plus 1 zeros on a b interval. I hope you understand this. You keep doing this. So if you consider the double derivative, then you can find at least n zeros on this, and we keep doing this, right? So if you consider the n plus 1 derivative of phi, then you can say here, so this has n plus 2 zeros on AB. If you consider the first derivative of that function, it has n plus 1 less than here. So 1 less than this number, right, for first derivative. So for second derivative, 2 less than this number. For n plus 1 derivative, how many? N plus 2 initially you have this many zeros, right, for this, and for this derivative you have n plus 2 minus the, look at the derivative here, n plus 1. You have at least one zero on this interval AB. Alright, so let's take that zero. Let's define that zero. Let's define that zero as psi, this one here. So let's call it psi. So we know that there exists a number psi such that there exists a zero in between a b. Let's denote that zero is psi, right? Then therefore we can say there exists a zero in between a and b such that this function vanishes at that point, right? All right, so now you plug this number into here, right? So yep, this is your, so you can find the n plus 1 derivative using this. What is the n plus 1 derivative? So what is the n plus 1 derivative, which is equal to n plus 1 derivative of f minus n plus 1 derivative of this polynomial and n plus 1 derivative of w, right? So you know that n plus 1 derivative is factorial n plus 1, and this because this one is a polynomial with degree less than or equal to n, this this becomes 0, right? Because Pn is a polynomial. Here Pn is a polynomial with degree less than or equal to n. So when you differentiate this n plus 1 times, that becomes 0, right? So this vanishes. You end up with having f here this one f n plus 1 derivative at this point, and this one here, right? So we know that this is equal to 0 and this should be equal to 0. Then we can find, we get this relation f of f n plus 1 derivative at psi is equal to c times w n plus 1 derivative of w at this point, right? We know that this one is equal to n plus 1 factorial. Substitute that yeah, you can substitute that yep, and you know the value of c. This is the value of c, right? So put that in to this equation. Putting that into this equation, you get this one. So f the n plus 1 derivative of f evaluated at psi is equal to this one, right? So now you consider y as an arbitrary value. There you consider y as an arbitrary one. Then you can put put x here, right? Arbitrary. So then you get f, so n plus 1 derivative of f evaluated at psi. You can solve this for w of x divided by n plus 1 factorial is equal to f of x minus p sub n of x. So here you plot. So what if you consider y as an arbitrary value? You can consider that you put this one, you replace y with x, right? So you get this one here, right? So this is in other words, this is your error, right? E of x is equal to 1 over factorial 1 over n plus 1 factorial times n plus 1 derivative of f evaluated at psi times wx. Wx is the product of these nodes, these linear factors. Finally got this. So here psi, so psi is a value in between a and b. So we through this theorem we have done this one. So I hope you understand how to prove this theorem. So this is the error between f and the interpolating polynomial. All right, I hope you understand this. Let's meet next in my next video.